soon as it's finished. So please be patient with us. And I may take a little time in the lecture to go over some of the problems, say next Tuesday when the test is being returned to you. But for today, we are continuing our discussion on boundary layer. I want to revisit what we covered, or the main concept last time, and tie in with the homework that's due today. And without saying, just make sure you upload the homework. That will be graded. And then we're going to look at drag coefficient. Mainly that's the table lookup, experimentally based observation of how one can estimate different objects, different Reynolds number, what is the drag. And those will be the next couple of set of homework. So I just want to make sure you have what you need to tackle those problems. And the half of the lecture will be devoted to the concept that we have loosely discussed prior, full separation. How does that relate to what we have seen so far? What happened? And how does that affect entering devices like an airfoil, like a diffuser, etc. And with that, that will allow us to explain why there are dimples on a golf ball. How does that relate to the concept of boundary layer and so forth? So I hope the lecture is kind of interesting and practical, and by all means, slow me down by asking questions. Assignment, reading of drag and lift, mostly it's just learning how to use those table and chart in the textbook correctly. And it's mostly experimentally based. There's not much theoretical background to it. Homework for next Tuesday, a set of 4 problems, 1 of 3 problems. And Mike will be posting those old edition problems hopefully by the end of today. My estimate is like 2 hours. I don't think I may touch on that just to make sure you don't take off in a tangent. Give you some framework as to how to tackle those problems. Another set of homework that is due a week from today. So, last time we talked about boundary layer, and we understand why it's so useful in that it allows us to make some estimation of the flow around an object like an airfoil. And the case in point first is that the concept of laminar to turbulent transition. So for the external flow of what we are dealing with in chapter 9, there's always a laminar flow to start from the very beginning of an object like an airfoil, a flat plate, a car hood, etc., etc. So I would like to relay this concept to your homework that's due today to estimate the boundary layer thickness on a car hood. So if you have done the homework, we're talking about a hood that is 5 foot in length. Flow is coming at 65 miles per hour, and you're sitting on a windshield looking down at the hood, at the nose, and ask yourself, what happened to the airflow as you go over this plate? And based on your analysis and based on the formula I gave you last time, to estimate the boundary layer thickness for a laminar boundary layer, we start at the nose. What we find is that, and this is approximated so that we can focus on the big picture, out of that 5 feet, approximately about a foot from the nose, we find that the boundary layer will go from laminar to turbulent. We call it the transition. And the thickness of that station, which is the formula you use to estimate based on the Reynolds number, is small. How small? A tenth of an inch. That is that shear layer on the car hood as they run down the highway. That you cannot see it, but because of all that shear and the drag and the frictional effect, that the engine of the car has to provide enough power to overcome. And beyond that, the boundary layer becomes turbulent, so this region is laminar. And then there's a transition region, and then beyond that, you have what is called a turbulent boundary layer that is very chaotic, unsteady. The air molecule, you can visualize it as dancing, doing somerset, talking to each other, mixing, whereas the laminar is very well behaved layers. And this plate can continue indefinitely. 5 foot would just happen to be the size of the hood. If it's an aircraft carrier, you know, the hull and the water that cut through the hull can generate a boundary layer much more thicker because the length is so much bigger. All right, but for an air over a hood, or eventually you have the windshield would disturb the flow. So this is a very simple-minded visualization of what happened to this so-called invisible boundary layer. Do you have a feel for that? So this transition is different from internal flow in the pipe, where the flow can be either purely laminar or purely turbulent inside the pipe. It always, for external flow, has to go through laminar to turbulent. And that has some important consequences to engineering devices, which we will alert to today. But so let me pause and make sure you understand this concept of transition on the external flow. Questions? Yes?
Does the transition region have like a finite length?
Yeah, it's a very good question. For what we do for homework, for simplicity, first and foremost, we pick a number, 500,000. That's wrong. In real life, that can range from anything from 1/10⁵ to a couple of millions. All right? It's very much problem dependent and it goes beyond the introductory level. As an example, it depends on how quiet or how unsteady the free stream flow is. That's just another parameter that we don't have time to deal with. So this is not a magic number, number one. Just like the internal pipe flow transition, there's a range. It's not 2,300, it's like 1,000 to a couple of thousands. Number two, this region here is not on and off type black and white. There is a transitional region in the size of this problem. It could be about a 1/10 of an inch or maybe half an inch, where the flow will slowly go from a laminar eventually to a turbulent flow. So the study of this type, very simple-minded flat plate boundary layer, have been studied over many years. In our wind tunnel next to Randolph, there used to be a professor whose career is to study the transition on the plate like this. Right? You would think that after 50, 60 years of research, all the problem has been done, but no, it's still a very active research area. And I will tell you some later on some story as to why it's so important to know where this occurred and how it occurred. All right? There was another question? Yes?
So if we're not given a critical Reynolds number, do we just assume 500,000?
Yeah, that's correct. For our purpose, we're simple-minded, you know, just for the purpose we have a graded answer to grade the homework. We take 500,000, unless we were told otherwise. Correct. Yeah. And I will also emphasize all the discussion so far up to this point, for simplicity, is assuming no pressure gradient on the external flow. And today we're going to qualitatively look at this flow separation, which is because of the pressure gradient is not zero. The equation I gave you last time to estimate the thickness of this boundary layer is only applicable for zero pressure gradient flow. What does that mean, zero pressure gradient? If this is P1, what is the pressure at P2 downstream? They're the same, right? If they are not, the physics changes. And it becomes very interesting. Yes?
Why was the area given for this problem?
It's not needed, it's just the length. It's just typical car hood is almost like a square. The dimension into the board is inconsequential, it doesn't change anything. Right? It's mostly this dimension that we're talking about. So all the objects we deal with, a missile, an airplane, submarine, bicycle, have this kind of viscous effect that creates a drag. And then more to that will come later, can change to first order how the flow behaves due to the boundary that is separated. And that's the focus of today's lecture. Yes?
If our critical X value is longer than our plate, do our assumptions go out the window?
Well, if the plate is, say, only about 6 inches, then the boundary is entirely laminar, because it hasn't reached the point where it becomes turbulent. So that's a fair question, right? So I think this concept, I hope, is fairly simple to digest. The one that has some issue with, and someone asked me at the end of class last time, is now that we talk about transition, the next concept that we have to ingrain with boundary layer flow is the use of the Reynolds number. I'm a fluid mechanicist. If you tell me the Reynolds number of 1 million, 10 million, it means something to me. I can use that number to help visualize how the flow is behaving. How? For most practical engineering problem, Reynolds number is huge. Millions, tens, hundreds of millions. large object like a ship, the automobile at very reasonable speed, Reynolds number is very large. So that's 99% of our engineering problem that you pay to solve. For that, this boundary layer concept is very clear and applicable. And it created this invisible shear layer. Within that dash line, viscous effect is dominant, very important as the inertia effect. And I cannot use Bernoulli. Why? Because it's viscous. Why? And then I can assume for the rest of the flow field, I can now create an airfoil that has the shape of the dash line, because that's what the flow is seeing. And the rest of the flow, beyond this dash line, I can pretend that it's invisible. Euler's equation is just one mean of solving that flow field in the most simplistic way. The other way is the equation of motion, which we haven't dealt with in 3D, but neglecting viscosity, meaning the Euler's equation extended to 3D. There I can use to solve the flow field, because then I can assume there's no viscous effect. There was a question in the back?
Yes. For something like a ship where you have it going through air and
Yep.
through water,
Yep.
how does...
So for a ship, you think about the physics, right? I think you should know how much is the viscosity of water compared to viscosity of air. Water is much higher, so all you care about is the wetted surface of the ship, right? The shear it creates, which is what we call the frictional drag, and also the form drag, the wake created by the ship when it passes, pressure is lower, and the difference between the pressure up front and the back create another drag. What kind of drag we call that? There's a name that goes with that from last time? Pressure drag, or we call a form drag or shape drag, because it's very much a function of the shape of that object. Like a fish, a streamline, the shape, a missile has very little form drag. But the longer the object, the more shear you have, and the more frictional drag. So as an engineer working for Boeing, you're trying to design an airfoil that is optimum, minimum form drag and minimum shear drag. And then you will have less power required from the engine to fly at constant speed. There was another question?
No.
Okay, so those are all important concepts. So this is easy to digest, the one that some of you may have problem with. And this is a new nomenclature that we'll use repeatedly for the next few weeks. This is called order of magnitudes. All right? And we will use this symbol, a zero or order of within parentheses. So what this reads is that what happened to the Reynolds number is in the order of 1, or even 10, or even 100, even 1,000, but not medium. What happened then is the viscous effect is equally important compared to the inertial effect. Neither one can be neglected. And with that said, then you don't have now anymore a thin, small boundary layer. That concept breaks down. So with the same airfoil, whether the size is much smaller or the velocity is much lower so that the Reynolds number is small, this so-called boundary layer becomes almost the entire flow field. And within that, the poor foot file, while it's flapping the wing, is both equally challenged by the inertial effect, which is the apical MA type flapping motion, and the viscous effect. So it relies you swimming in motor oil, very viscous fluid, or swimming in gelatin. Right? Every stroke takes extra effort. So when the Reynolds number is small, like you see in your homework, there's no such thing as a boundary layer. The entire flow field has to account for both viscous and inertial effect. Is that clear? All right, so those are very much elementary concepts that form the foundation of what we will be able to tackle in more complex problems. So the homework is done. I don't think there's much problem in the, or I could be wrong. Is there any question on the homework? Yes?
So for what Reynolds number do we consider there to be a boundary layer?
Anything that is less than a couple of thousands. Again, it's a gray area, but when you are in 500,000 Reynolds number, for sure you can assume the concept of boundary layer can be used. All right? But a couple of thousand is very, very programmatic. If you want to be safe, don't use the concept of boundary layer. Meaning that if you are interested in analyzing this flow field, you can make no assumption. You're going to have to tackle the full viscous equation of motion, which is very nasty, which is very difficult to solve. Okay? And that's why this assumption back in the 30s, 1930s that is, can allow engineer in Germany to create much better airfoil. The higher lift, the less drag. Just because of that simple concept of breaking down the flow into two regions. Okay? And that's why it's such an important topic in fluid mechanics. Okay. I just want to touch on the problem where the plate is oriented at an angle, and this is a little bit detailed. I think the problem of resolving the drag and the lift is actually quite straightforward, nothing but geometry. What I want to use this to illustrate is the direction of the forces between the shear acting on the fluid versus the shear acting on the plate. All right, it's a little subtle, but I think it's once and for all, it's important to see the distinction. So if I draw just a blow-up of the dynamic or the action and reaction of the forces on the fluid due to shear and no slip condition. Here's the boundary layer. I leave a little gap between the plate and the velocity profile so I can show the direction of the forces. Which direction is the force acting on the fluid in order to slow it down from that free stream velocity to zero velocity? You know, if I ask you to draw the direction of the shear force on the fluid, on the air, which way does it act? Parallel to the flow, along the plate pointing to the left, or downward in the same direction as the flow? Do you understand what I'm asking? Which direction will the shear work act on the fluid? To the left or to the right? Yes?
To the left.
To the left, yep. That is how I can slow down the flow to zero velocity. So the shear on the fluid, just like friction. Think about friction. This is exactly what it does to a block that's sliding along this inclined plate, but except now it's a deformable fluid. But the shear acting on the fluid, on that air or water, is pointing in the opposite direction of the free stream flow. Action and reaction will tell you then what is the shear acting on the plate. Exactly opposite. And I use the subscript W to designate the wall shear, which is equal and opposite to the fluid shear. All right, so if you look at that and you consider all those elements on the plate, that's all pointing in the direction of the flow. So those are shear on the wall, on the plate. You sum them all up, add them all together. Now you have an equivalent effect of this airfoil and an angle attack, of which, if you sum up all that shear, will give you the total shear drag, the drag that is due to friction. Okay? And it's tending to push the plate away from the flow, in the direction of the flow. So to overcome that, your engine, if this is an airplane, must produce enough thrust in the opposite direction, pushing it forward to maintain constant speed. And that's how the action-reaction play itself in the detail of how they interact in terms of the direction. So it's very subtle, but I thought it's important to make sure you understand how they act on the fluid versus on the plate. Question on that? Okay, lastly. airplane that's flying at 400 miles per hour at 1,000 feet versus at sea level steady. And this is a real life engineering problem that I want to relate to you because it's a very expensive problem. The difference, assuming you have done this problem, at 10,000 feet, you find out that the location where transition occurred on this airfoil is roughly like 2 inches, right? You have done the problem, and I think that's what you find. And I'm approximating the number to focus on the big picture. At sea level, which is on the carrier deck, for example, or airplane taking off, versus a cruise, due to the change in the viscosity and the density, and hence the Reynolds number, the location of transition is off by not much, half an inch. Do you think that will have any consequences on the performance of this airfoil? It turns out the answer is very much so. A seemingly so innocent of a half an inch difference on an airfoil can cause substantial performance on components. And the case in point is in the aircraft gas turbine engine. And this is the part that come out from those engines. This is a turbine section which is behind the combustor of an aircraft gas turbine engine. And what is a sector of 360 degrees immediately behind the combustor, where the hot gas is accelerated to very high velocity so that the downstream component, which is a rotating turbine, can extract the raw power. This is not external flow, but it is still an airfoil. And the phenomena that occur here, where the transition is off by small amount, let's say